Hello everyone, my name is Aarohi and I'm a graduate student at Cal State East Bay. And today I'm going to be talking about my research topic, can ion exchange resins be used to remove boron from produced water and increase water sustainability? Let me first tell you what motivated us to do this research. Hydraulic fracturing is an unconventional method to extract oil and gas, and it uses around 2 to 13 million gallons of water per well for drilling. There are around 300,000 wells in United States, and this water usage affects areas with dry climate like California, Colorado, and Texas while extracting natural gas. Along with this natural gas, we get produced water that has high concentrations of salts and metals, and our target is to remove boron from this produced water. You would wonder why specifically boron? Well, even though boron is an essential micronutrient, it can be toxic to plants above 0.5 milligrams per liter. Since produced water have high concentrations of boron, it is important to remove boron from produced water before reusing it in agricultural field. Here's where our research comes in. Our focus is to remove boron using ion exchange resins. Well, now you would wonder, why choose ion exchange resins? Well, there are three reasons. First is that boron species have high affinity for ion exchange resins at different pH. For example, if you see this picture, boron binds well to the resin. The second is that the use of resins consumes less energy and produces less carbon dioxide than other technologies. This helps mitigate climate changes. And third is, boron can be recovered and reused in other industries. This helps with cost effectiveness. Let's talk about the research objectives. We have three objectives. First is to compare boron adsorption at two different pH values in millipore water. With this, we can find at which pH level we have higher boron adsorption. And then using that pH, we try to evaluate resin effectiveness in produced water and characterize interference by other species. This can show if there is any decrease in boron adsorption. Lastly, we evaluate boron adsorption in produced waters for a variety of resins and as a function of boron concentrations. Let's see materials and methods. For the materials, we used media such as Entera produced water and millipore water, boron stock solution, buffers, Hawk boron reagent, and different resins. Now let's see the methods. First, I prepared 1 molar of buffer solution in media. Then I made 600 milligrams per liter of boron stock solution. Then I set up 2 sample sets with increasing initial boron concentration. Later on, I added 0.5 milligrams of resin to one of the 2 sample sets. Then, overnight boron adsorption was allowed at 30 degrees Celsius. And next day, samples were centrifuged for 30 minutes at 25 degrees Celsius. Finally, the supernatant were collected for analysis. The supernatants are mixed with boron reagent and then analyzed on spectrophotometer for colorimetric assay. This is the last step for the method section. Now let's see the results and discussion. First goal was to compare boron adsorption at 2 pH values. The media used was millipore water. The pH tested were pH 7 and 8.5. Initial boron concentration was 0, 60, 120, 180, 240, and 300 milligrams per liter. And the resin tested was Emberlight IRA 743. let's see the graph here. On the x-axis, we have residual boron in the sample, and on the y-axis, we have adsorbed boron in the sample. All data points are fitted with Langmuir isotherm. Looking at the results, we can see that pH 7 shows better boron sorption at higher boron concentrations than at pH 8.5. This can be determined by the Qmax value, which is almost double for pH 7. The Qmax value suggests maximum adsorption value for a resin particle. Our second goal was to see boron adsorption at pH 7 in produced water. The media this time used were millipore water and Antera produced water. The pH was kept 7, initial boron concentrations were kept same as before, and the resin was Amberlite IRA 743. Looking at the graph here, we can see that Antera shows better boron sorption than millipore water at higher boron concentration. This means that there is little chemical interference by other species in Antera produced water, and this suggests that boron adsorption doesn't decrease in Antera produced water. This also shows that resin is highly specific towards boron. Last goal was to see boron adsorption in produced water with different resins. The media used was Antera produced water. pH was 7. Initial boron concentrations were same as before, and the resins used were Amberlite IRA 743, Resintec SIR 150, Amberlite PWA 10, and Purolite S108. From the results here, we can see that all resins are efficient up to 180 milligrams per liter of boron concentration. And then as we increase the boron concentration, Amberlite IRA 743 is more efficient than the other resins. This can be determined from the Qmax values given here. So we can see that boron removal with ion exchange resin shows boron adsorption is higher at pH 7 than at pH 8.5 in millipore and produced waters. There is little chemical interference from other chemicals present in produced waters. For the resins tested, Amberlite IRA 743 works most efficiently at high boron concentrations in produced water. And from this, we can summarize that ion exchange resins are a promising technology to efficiently remove boron from produced water. I'd like to thank my mentors and all the people who have helped me and given me the opportunity to present my research. Thank you so much.